Thanks very much. So once again, thank you very much to Jingyue and Rosanna for this very kind invitation to myself and Ina to give this talk today. The talk has quite a cumbersome title, as you can see, but what we're really going to be telling you about over the next hour and taking your questions about is this cyber digital twin that we've been building at Facebook in our team that simulates user communities on the Facebook platform, and that allows us to tackle all sorts of problems that cover reliability, integrity and privacy, as you'll see. And although it's Ina and I giving the talk today, this is joint work with a great many people at Facebook who are listed here. I hope we've included everyone. My bad if we didn't. And just to mention that for most of the talk, we're going to be talking about the work of the London probability team, who's building this cyber digital twin, which we call DubDub. That's WW. It's kind of a cut down version of the DubDub platform at Facebook, which is hundreds of millions of lines of code. And we build a simulation that sits on top of that. So in the talk today, you're going to be hearing about industry and academia a little bit. Before we get stuck into talking specifically about DubDub, this is because the organisers asked me to talk a little bit at the beginning about my experiences of working in industry and academia, having been a professor and also more latterly an industrialist. And so we're going to be covering this idea of digital twins and why we think that there's this specific concept of a cyber digital twin, which is different from a cyber physical digital twin. And this is where the software engineering community really has some potential. We're going to explain in some detail how our simulation platform works at Facebook and some of the technical and scientific challenges that raises. And in particular, we're going to be focusing on the challenges of testing a cyber digital twin. Testing a simulation system is essentially one of the most challenging testing problems in software engineering for reasons which I'm sure you'll appreciate in terms of test flakiness and non-determinism and the unknowable oracle. But we'll go into some detail on that. Ina will be explaining about the simulation platform and metamorphic testing. So before we get started, as I mentioned, the organisers asked me to say a little bit about my experience of working in industry and academia. And my first experience of industry, if you like, was trying to start a company when I was at school. And my second experience of industry was being at Facebook. And in between, everything has been academia. So I'm not really the world's most experienced industrialist by any stretch. But I'll give you the benefit of my thimbleful of industrial experience, if I may. So it's kind of curious because when I started this first company with two friends at school, we were making computer games. This was my game. And we were literally printing the cassettes ourselves, recording these cassettes with the games on the night before the computer show where we tried to launch our product. I think I made about 200 and we ran out. We weren't able to sell anymore because we'd run out of these cassettes. And so what happened was this company, Sunshine Publications, bought our company and our games, and they marketed them. And the thing I learned from that was that actually the best exit strategy for most companies, certainly most startups that I might be involved, is to be bought up by a bigger company who's got much more expertise. They were the ones who made this cassette insert cover for the game, which I'm sure was very instrumental in its sales. I don't want you to focus on the rather garish graphics, but perhaps just on the cassette insert. What they wrote about the game was curiously prescient for my career because they said it's more like a simulation than a game. So back there 38 years ago, I was building what laughably could be called a synthetic world. This is what it looked like. It's not so exciting. Computer graphics in 1983 weren't great. They were, you plugged your computer into a television screen and this is what the graphics looked like. So not the world's greatest game. People used to follow me around the playground at school, taking the mickey out of me, doing these kind of clicking sounds with pretend swords. The only real thing I can claim from this game into any kind of contribution, if I might even dare to call it that, is that there was a survey of computer games that said that this was the first game that involved replaying a game and recording it on backing store and then being able to replay the game afterwards. And curiously, 38 years later, we've been trying to tackle problems of non-determinism and implementing something quite similar to capture and replay what our bots do in our simulation. So that was my first experience of trying to actually essentially make money from software engineering. And for the 25 or 30 years in between, I was an academic. But as Rosanna mentioned, we started another company to sell testing software. And we were very fortunate once again to be bought up by a much bigger, smarter, sensible company who knew how to use this technology, and that was Facebook. And as a software engineering professor, the exciting thing about being acquired by a company like Facebook was the tremendous scale. I'm sure at the EASE conference, throughout the talks, you'll find that this theme of scalability permeates a lot of what we do in software engineering. And the scale at Facebook really is quite daunting and also exciting. So let me give you some numbers to give voice to that scale. So 1.84 billion people every day use these products. It's probably one of the most used pieces of software ever designed. That's 2.8 billion people monthly using one or other of the Facebook products. It's almost a third of the population of the planet, and many more if you consider the ratio of those who are actually on the internet at this point. But from a software engineering perspective, perhaps the more interesting number is that there are more than 100,000 commits to the repositories of code per week. And so our job is to try and make those more reliable and to tackle other issues concerned with, say, integrity and privacy. And we use simulation to do that. So we'll be talking about that later on. But what we did in the company that we bought to Facebook was we deployed this technology called Sapiens. And Sapiens is a technology for searching the space of inputs to try and find those that will crash the app. So it's a client-side testing technology, loosely based on search-based software engineering, with a lot of other bells and whistles added to make the search more effective. And it runs on emulators, and this is roughly what it looks like when it's running. This is a small snapshot of the overall space of emulators. Each row shows a different product, so Facebook on iOS or Facebook on Android, Instagram, Messenger. And what you're seeing is the process of searching for those inputs that will make these emulators crash. And of course, if we can find such a case, then that means we've likely found a case that will crash a real product, say a real Android device, and that will get reported to the developers who try to fix the bugs. So there is a paper about this. I don't want to spend too long on it because we've got other things to talk about today. But what I really did want to mention is how you can get involved as academics in industrial work. And I want to highlight a specific case study here of a PhD student, Alexandru Marginian, who was doing his PhD at UCL, and then he came and did an internship at Facebook in the Sapiens team for 14 weeks. This is a standard period for an internship. And what he did was he deployed a technology called SapFix. It was based on his PhD work, but it took the test cases that Sapiens automatically designs to test these apps that I just showed you, and it added to them the ability to automatically repair certain class of bugs. He went after null pointers because that was our most commonly found bug, and that's also the most commonly found bug in practice. So I just want to give you some sense of the potential you have. If you're a PhD student thinking of coming to do an internship at Facebook or another large tech company, or if you're a professor who has a PhD student, you're thinking like, well, should I encourage them to do this? Let me just illustrate. In those 14 weeks, Alexandru worked on this SapFix product. I want, if you could just raise your hand, or I think on, you can do this virtually on Zoom by raising your hand to say if you've used any of these products on your phone. Yes, I think several people, quite a few, maybe a third or half of the people are putting their hand up. So if you've got Messenger or Facebook or Instagram on your phone, then you are running software that has been automatically fixed by Alexandru's work in his internship. And it's been automatically fixed to fix bugs that were automatically detected by Sapiens. So this is an end-to-end technology that essentially finds and fixes bugs and has actually affected the code that's running on your phone right now. So as a PhD student, I couldn't have dreamt of the idea that I would, within a few months, be able to say that my PhD work was affecting billions of people around the world, and have the chance to go into almost any room of people and say, have you got this product on your phone? Ah, my research has affected that product. It's affected what's actually in your pocket. So I think this is tremendous. It's tremendous potential for PhD students to have impact. And if you are a PhD student, I'd really encourage you to consider doing an internship at a company like Facebook. Okay. let me move on. So he also worked with the Infer team, and so there's also lots of opportunities as a PhD student to work together. So let me move on from that to tell you a little bit about how we do simulation at Facebook. So if you consider the Facebook infrastructure, processing devices and storage, what we do is we deploy bots on top of that infrastructure. The important thing is that the actions the bots perform and the observations they make are all made through the real infrastructure. So if one of our bots sends a message to another bot, it does so through the full stack, all those hundreds of millions of lines of code in the backend infrastructure. And we reward our bots for being bad to other bots. I should mention that all the interactions, of course, are between bots, and they're kept in a completely isolated sandbox world, this world that we call dub-dub. But the important thing is that we're rewarding these bots for behaving badly so that we can simulate harmful behaviors on the platform. There is a research paper about this that appeared last year at an ICSI workshop in genetic improvement. And at the EASE conference, in your proceedings today, linked from the web page, there is an updated position paper about our dub-dub simulation. So you can read more about it there. So I want to illustrate why we do this in terms of the kinds of harmful behavior we might see on the platform. And in particular, let's focus on scamming type behaviors and why it is that we care about detection rather than prevention. So let's consider an analogy. Suppose you're driving along the road. It's a lovely sunny day. You're enjoying the summer. You're driving along in your camper van, and suddenly coming shooting past you, nearly knocks you off the road, a car speeding way past the speed limit. What can you do? As the driver of the camper van, there's very little you can do. But as the provider of the road infrastructure, there's quite a lot. We call this mechanism design. You design the mechanisms by which your customers interact in order to try and make these harmful behaviors difficult. You might try and detect the harmful behavior. So in the UK, this is what a speed camera looks like. Or you might try to prevent the harmful behavior by putting speed humps into the road. Interestingly, in the UK, cameras are painted bright yellow like this because although it's a detection technology, we actually want to try and make it into a prevention technology, because clearly prevention trumps detection. So how does that play out in the case of mechanism design for dub-dub bots, where we're trying to reward these bots by crawling? What we do is we interpose in these actions and observations that the bots perform the software equivalent of those speed humps. What we do is we have rate limits that affect how often or how many of the actions you can perform and how you perceive the results from the Facebook infrastructure as observations. And those affect each of the bots in different ways. So each has its own constraint vector, if you will, that affects how it's going to perceive the infrastructure. So perhaps this bot can only send 4 messages, it can only receive 12 per minute, it has to leave a 17-second gap between each message. This bot has different parameters for those same constraints, and maybe the third bot shares some of the properties of the second and the first bot. So those of you who are familiar with evolutionary computation will see immediately here that what we can do is we can essentially mix and match. We can breed the bots' constraint vectors to have them combine and reproduce to produce new constraint vectors. And this really alludes to the idea that what we're talking about here, this constraint vector, is a search space. It's the space of possible simulated changes to the products we could perform. So ways in which we could have changed the product infrastructure in this search space. And what we're searching for is those tiny, few little nuanced, subtle changes that will tend to make it hard for bots to achieve the harmful behavior, but easy for bots to achieve normal behavior. And the reason this can work for us is because harmful behavior is essentially misusing our products to try and achieve things for which they weren't originally designed. So it's a very specialized kind of behavior. And if we formulate that as a search problem, then we can use computational search techniques. Essentially, what we're talking about here is searching for a needle in a haystack, but the software engineering community in particular has developed lots of techniques for doing that. The area generally known as search-based software engineering is all about this problem. How do you search these large, complicated constraint spaces in software systems? And in our case, it's a multi-objective problem because we want to simultaneously inhibit the harmful behavior while at the same time encouraging, or at least not hurting, the normal behavior. So that's a bi-objective constraint solving problem where the search here, the two fitness functions are in opposition to each other. And that's a classic search-based software engineering problem. The reason it's good to do it in this way with this mechanism design layer is because changing the products themselves would involve recompiling that whole back end of hundreds of millions of lines of code. So build times could run into tens of minutes easily half an hour. And other companies have reported this problem too. But by doing the search at this mechanism layer, we're essentially simulating hundreds of thousands of possible product changes in very short periods of time compared to the problem of recompiling the back-end infrastructure. So I just want to mention that we do have a funding call for research in this area. We launched this at ICSI last month. We call it an RFP, Request for Proposals, on agent-based computing to tackle these integrity and privacy issues. And I'd love to encourage you to apply. I've been, as we talked about at the beginning of my part of this talk, I've been an academic as well as been in industry, and I know how hard it is to get funding and how painful the process can be. And I want to say that we've tried to bake into our process for this funding call the understandings that we've learned from talking to the academic community about funding. So the deadline is the 7th of July, but you only need to submit 2 pages. It couldn't be more light touch, really, as a funding process. You ought to be able to complete a funding application in an afternoon. We're not offering a tremendous amount of money by comparison with, say, the large EU projects or the NSF projects. You know, it's up to $100,000 per project, and we'll fund up to 5 of these. But although it's not a life-changing lab reformulating amount of money, you do only have to put in 2 pages. And the other thing is, it's an unrestricted cash gift. So as a company, we will make no constraints on how you spend that money to support your research. You can spend it on anything you want in your lab that will help your research. As a former professor, I know how valuable that is, because most of the money we get to support our research is very strongly typed. And it's very difficult sometimes to find money to support those relatively small but very important things that keep a lab going, but for which no funding agency currently provides specifically typed money for that. So an important thing about this, as well as the light touch application process, is that it is an unrestricted cash gift. We will probably invite you to come and give a talk about your work at Facebook at a workshop we'll organize, and we'll pay your expenses for that, but there'll be no obligation for you to do so. Last year we had a similar call, but we were offering up to 50K that time. Now it's 100K, and we hope to have another call next year and to move from this position of offering unrestricted gifts to actually developing much closer relationships with a few key partners for building out this agenda of automated software engineering for cyber digital twins. So this platform that I've been telling you about is actually a cyber digital twin of the Facebook platform. So let me tell you a little bit more about why I mean it's a digital twin. So when we talk about digital twins, what we're thinking about here is, imagine the scenario where you built some software to simulate a car. Then what you've really got is you've got a model of the car. We call that a simulation typically, and simulations have been around for many, many years. So suppose further that simulation is informed by the behavior of the car. So there's sensors on the car that inform the simulation, and also the simulation itself could be used to inform the car. So now suppose that we automatically inform and are informed by the physical product itself, the car in this case. Then our simulation now becomes a twin. The difference is, because it's automatic, we could actually imagine that this cyber physical digital twin got deployed into the car. In fact, when I was a professor, I did work with people at Daimler who did exactly this. They deployed models of brake controlling systems into cars in order to be able to simulate the car system as it's operating and then make decisions. So this has been something that's been studied for many years, but has come to be known as cyber physical digital twins. And it's a very important and exciting research topic. But it's important to note that we're talking about cyber physical here. So it's a boundary between the cyber world and the physical world. Dub that we've built is a digital twin as well, but it's not a cyber-physical digital twin. If we imagine building a software simulation of a software system, then what we're essentially doing is we're building a cyber digital twin, and we can deploy that software simulation inside the software we're deploying in exactly the same way we might deploy a braking simulation inside a car. But because it's cyber, we now have the possibility to have a hierarchy of simulations, each deployed inside each other. So a cyber digital twin is a fundamentally different type of digital twin to a cyber-physical digital twin, precisely because we can have this hierarchy where each layer of the simulation informs the other layers and is informed by it. And we can't do that with cyber-physical digital twins because there's just the one possibility for deploying inside the thing you're simulating. Whereas with a cyber digital twin, you can have this hierarchy. And so with that, I'm definitely now going to hand over to my colleague, Ina, who's going to tell you more about how we build that system at Facebook. Thank you very much.
Yeah, thank you very much for having me here. And now I would like to walk you through the relation of digital twins to DubDub platform. DubDub has different modes of the simulation. The online mode, which is built on top of the Facebook platform itself, is our most faithful simulation of the Facebook platform, where all bot actions are executed on the Facebook platform. The offline mode, DubDub does not necessarily execute all of the bot's actions, nor provide all of the observations to the bots that are available on the Facebook platform itself, but instead uses either synthetically generated content or recapture and cache the online simulation result for subsequent users. And on top of that, we have emulator that gives computational search over the space of product changes guided by the fitness functions and capture the impact of the product changes on normal and harmful behaviors. The simulation hierarchy introduces classical engineering trade-offs between the precision and speed. So DubDub employs two strands of simulation. The first strand on the left-hand side of this diagram is the cyber-physical simulation of the real users by bots. The second strand to the right-hand side of this diagram is the chain of cyber simulations, which simulate at the Facebook platform. The interaction between the bots and the simulated Facebook platform is cyber interaction, which simulates the cyber-physical interaction between the real Facebook user and the real Facebook platform. And all of the modes are implemented using the environment, which is a component in DubDub platform. And while speaking about the component, I would like to expand a bit more on the architecture of DubDub. There are four major components of a DubDub platform. The first one is scheduler. The scheduler dispatches events at the appropriate simulation time and is responsible for terminating of the simulation. Once an event is scheduled and is ready to be executed, the executor component comes into play and sends the request to an environment service, which I mentioned is one of the modes of the simulations. Executor is responsible for sending requests and handling its responses, including the exception handling. The environment. The interface to Facebook's environment is provided by the API for Actions Execution, which is implemented as a thrift service. The environment service can be implemented for different platforms or as synthetic environment, the one that we mentioned before, the offline mode. Just a very quick note on the thrift. Thrift is an interface definition language and a protocol used for defining and creating services. So it allows software written in different languages to communicate between each other without knowing implementation details. So that's the main benefit of this architecture. And the policy. The policy is responsible for selecting agent actions based on the observations from the environment and for maintaining the state of the execution. Agent actions can range from hard-coded stochastic rules to adaptive actions based on the reinforcement learning. And the policy also maintains the memory of the bot and also is responsible for the content generation. So now I would like to walk through the flow on an example. Let's imagine that we do have a simulation where bot A sends a message to bot B. So scheduler dispatches an event to send a message from A to B. Then executor translates the request to the thrift call to the Facebook environment where it's executed. And observations and available actions are processed by the executor. And then the policy makes a decision to send a message. And the scheduler, this event is put back into the scheduler's queue. This architecture has features like plug and play, flexibility, and scalability. And I would like to start from the plug and play. Policies can be reused in any simulation, and different platform policies can be applied to the same dub-dub simulation. As mentioned before, agent actions can range from hard-coded stochastic rules to adaptive actions based on the reinforcement learning. And I would like to look at two policies. The first one is replay, which is policy that follows hard-coded rules. And the second one is a community creation policy, which uses statistical properties. So one of the simplest simulations is actually replay policy, where we know all the actions in advance that needs to be executed. So replay policy is an example where real time and the virtual time comes into play together. That makes it a simulation time. So the virtual time is the timestamp used when simulation doesn't need to follow the passage of the real time one-to-one. And the real time is simply wall clock time. So let's consider an example where we need to simulate a story where a bot is streaming the video and their friends are reacting and commenting while streaming is happening. So here we need to make sure that the real time of the event is respected, and friends of the bot are commenting on precise time frames, not right in the beginning, all in one go, not right after, all in one go, but actually precisely on the time frame. That's why we need to make sure that we are using the real time. But after the real stream, the video stream ends, we can utilize virtual time, because now there is no link between the time frames for the video. Hence, all this matter is the order of the event. So we can put virtual timestamp any. Now, let's move on to the community creation policy, which is based on statistical properties of the real communities at Facebook platform. So the initial action, which kicks off the simulation story, would be the graph generation. Then each bot would be assigned a persona, which has properties like age, location, behavior. And then the bots will start to follow its policy based on the statistical properties. For example, 20% of users would create a group, and 90% of times bots would reply to a message sent by a friend, and 100% of time bots react to a post created by a friend. That's what we do. We always react to our friend's post. Now let's move on to flexibility. So the environment is implemented as a thrift service, as mentioned before, which provides the Actions API. The environment service can be implemented for any platform, allowing a simulation story to be run on different platforms like Facebook, Instagram, WhatsApp. So when dub user wants to run a simulation story, which is policy to create communities on Facebook platform, we can use Facebook environment service. When running a community creation story on Instagram, all is needed is just change a parameter, and we're going to be creating communities on Instagram. And when one wants to run a simulation story in offline mode by using synthetic environment, as discussed in hierarchy of simulations, we can also do that using the different environment, completely synthetic. This architecture also brings the benefit of scalability. The environment service is deployed on multiple machines and can be scaled when needed. Some simulations require 10 actions and can be executed on few machines. But right now, in production, some simulations are making millions of action requests to environment service. And now, as we walk through the architecture of DubDub and the hierarchy of the simulations in relation to the digital twins, let's move on to how to test simulations. While working on DubDub, we faced two major challenges with the testing of the simulations, which are stochasticity of the simulation and constant change of underlying data. Before we're gonna go deep into DubDub testing, let's briefly look at what metamorphic testing is. Metamorphic relation are necessary properties of the intended functionality of the software. For example, let's assume we wrote a program that implements sin x correct to 100 significant figure. And the metamorphic relation for the sin function would be sin x equal to sin 2 pi plus x. So there's been previous work on the application of metamorphic testing techniques to real-world software systems. However, although metamorphic testing has been a research topic for more than 20 years, there have been few other previous industrial deployments reported in the literature, and none that has been deployed into the continuous integration system. So metamorphic interaction automaton, MIA, is therefore the first deployment of the metamorphic testing into the full-scale industrial continuous integration system. And this work has been presented last month at ICSI, and as of 2020, Google and Facebook deployed Metamorphic into production. Just wanted to highlight that this work has been done by many amazing engineers that I have a privilege to work with, and all names are mentioned in the paper. So now, as we discussed metamorphic relation, I want to show some of the examples of metamorphic relations in DubDub in MIA. But before doing that, let's take a look at the simulation, which we call bot traversal of social graph. And then I'm going to show how we are using this simulation and how we are testing this simulation. So this simulation is very simple, and it consists of three types of actions. The initial action to search for the first user, initial user, then to view bot's friends, and then to send request to the bot's friend. So the output of the simulation would be the trajectory that consists of simulated visited friends on the platform. And now let's look at some of the examples of metamorphic relations. At first, let's look at the relation based on the behavior. So in DubDub simulation, all bots have personas, as mentioned before in the community policy. And for example, some bots have to imitate harmless behavior. Unfortunately, there is harmful behavior on the platform as well, and bots do need to imitate it as well. And in simulation hierarchy, there are different modes, as mentioned before, and one of the most faithful one is the online mode, where all actions are executed on platform, on the Facebook platform and Instagram. So when running simulation story in online mode, with the same setting, with the same bot behavior, one would expect to have the output trajectories as the same. But in reality, what our team observed is that trajectories can be different. That brings us to the test flakiness. A flaky test is the test that can be true or false even when circumstances didn't change. And there's been a lot of research recently on how to tackle test flakiness. So there are two few factors that contribute to a test being flaky, and some of them are real-world state change and inherent infrastructure non-determinism. So while some of them are extremely hard to overcome, others are easily solvable. So in online mode, we are operating with constantly changing data where graph and properties of the graph can change. Let's say new friendships are made, some friendships are lost. In offline mode, simulations always run on the static graph. That is very unlikely to change. So when running in offline mode, we are sure that underlying graph would remain static. Hence, simulation results in the form of trajectories would be the same. And now let's move on to the metamorphic relation that is based on the behavior and with the rate limit. So the very important concept that Mark already explained is mechanism design. In dub simulations, many mechanisms denote rate limits. The limit on the rate at which some particular actions or observations can be performed. Example would be a rate limit on sending spamming messages or friend requests, like example described in the talk. The key insight is that rate limits tend to have an overall monotonic effect. The more we tighten the rate limits, the more the behavior became constrained, with the result that observable properties tend to rise or fall roughly monotonically with the increase in rate limit. So in our crawling example, the tighter the rate limit is, the less harmful action bot can perform on the platform, and the more trajectories of the actions of the bot would look similar to the harmless bot. And by tightening the rate limit, bots don't have any other choice as to follow the trajectory of the harmless bot. So we would have guessed that having the two behaviors, harmful and harmless, the trajectories should be the same. Intuitively, we can reason about this as the more restricted the rate limit is, the less choices they have to act as a harmful bot. And the last metamorphic relation I wanted to talk about today would be based on the bot personas. So let's consider two bots, one in their 20s and one in their 50s. On average, social graph of the person has majority of their friends within the same age group. So the metamorphic relation would be the average age of simulation story trajectories from the bot in their 20s should be less or equal to the bots in their 50s. And I also wanted to mention that MIA covers different aspects of testing, not only metamorphic testing, but also end-to-end testing and the regression testing. So our team didn't have to write tests in 3 different systems. And in summary, what we've been talking today, as Mark has shared his industrial and academic experience, and we walked through the digital twins and how this concept is applied to dub platform. And we briefly looked into dub architecture and main concepts like scheduler, environment, and policy, and looked at MIA system and how